everyone. Okay, let's get started with 8.3, motion of charges in a magnetic field. We saw in the last section that a moving charge in a magnetic field will experience a magnetic force that comes from the cross product of QV, velocity, cross B, the magnetic field. So what that means is that the magnetic force is always in a dimension that's perpendicular to both the velocity and the magnetic field. So let's look at what that means for the motion of charges in the field. Consider a charged particle moving in a uniform magnetic field, and let's first look at the work. So if we calculate the work done by this force, we have dW equals F dot ds, or F dot V dt, and that has to be equal to 0 because the dot product of perpendicular vectors is 0, and we know that the magnetic force is perpendicular to the velocity always. So that's 0. The net work being 0 means that we have delta K is 0 from the work kinetic energy theorem. So this charge experiencing only the magnetic force will be moving at a constant speed. The force is always perpendicular to the velocity, and thus it cannot change that speed. So we have our charge. I've drawn something here moving at a constant speed. And you'll notice that this looks familiar. We've seen before when there's a net force that's only perpendicular to the object's velocity, and that produces uniform circular motion. We have a constant speed as well, so it would be uniform. And for now, we're looking at just the motion caused in that perpendicular direction. I'll talk in a minute about what happens when there's also a speed component that's not perpendicular, a velocity component that's not perpendicular to the field. Okay, so let's look at that perpendicular component. We can write the net force in the radial direction is FB, just the magnetic force. So QVB sine theta. This V sine theta is the component of the velocity that's perpendicular to the field. So we have V sine theta here. I put the V perpendicular sign to indicate that. QV perpendicular times B equals our net force in that radial direction, MAC, or mv squared over r. So relating this back to uniform circular motion. And then we can solve for the radius here. So this gives us an important quantity called the cyclotron radius. So when we have a charged particle moving in a magnetic field, it's called cyclotron motion. And there are a few different properties that we'll calculate for that motion. With that cyclotron radius, we can calculate the cyclotron frequency, the frequency of the revolution of that charged particle in the magnetic field. So just using V equals 2 pi RF, or this comes from 2 pi R over the period. So the radial speed moves 1 circumference of the circle per unit period, 1 time, which is 1 period. Okay, so rearranging for that frequency, we have that speed over 2 pi r, and then plugging in r here, you can see that it flips because it's in the denominator, and then that speed cancels, and we're left with F equals QB over 2 pi m, and that's the cyclotron frequency, and it's measured in hertz for a frequency. So the unit is hertz, which is 1 second inverse. All right, so two cases here. If the velocity of the charge is actually just perpendicular to the magnetic field, so there's no parallel component to the field, then this is the only components of the motion, and that gives us just uniform circular motion when we have the net force completely perpendicular to the field and no component of the velocity in the other direction. Okay. However, if the velocity of the charge has a parallel component to the field, if that is non-zero, then that parallel component will be unaffected. And so we've seen this before when we talked about the net force in the tangential direction for circular motion. So what happens is that this is now called helical motion, and it looks very helical if you look at these magnetic field lines. Charged particles will spiral around those magnetic field lines. So the components of the motion that's perpendicular to the field still undergoes uniform circular motion, but the parallel component continues forward at a constant speed. And that's what stretches out the circular path so that it begins to look like that. And there's a new term that's called pitch, which is the distance that the charged particle moves forward in one cycle of its motion. So as it makes one complete circle in that perpendicular direction, the distance it moves forward is the pitch. So that's a distance that could be measured in meters or any unit of length. And to find it, it's just using our constant speed formula. So this is the displacement, in a sense, equals that constant speed times the time. And since it's just one cycle, the time is 1 period. Let's look at 3 different applications of this motion. The first one I have over here is the northern lights. So we see the northern lights or the aurora because there's magnetic field lines surrounding the Earth, and it looks something like this. I've just drawn 2 there. And we know now that charged particles will follow a helical path and spiral around those magnetic field lines. So they spiral around those field lines and are directed closer to Earth near the poles. And near those poles, they're more concentrated and will interact with the gas molecules in the air, generally releasing light. All right, so let's move on to the velocity selector. This is a device that can be used to sort different molecules in a gas. And so for how it works is that we'll have charged particles sent through this velocity selector, which is a region of a uniform magnetic and electric field. So I've just drawn an example of one here. You can think of the uniform electric field as between parallel plates. So this positive and that negative plate there. And then the field goes from positive to negative. Those are the electric field lines, and these are the magnetic field lines going into the page. I've chosen them so that they'll both exert a force on this positive charge in opposite directions. But that could vary, but the forces will always be in opposite directions. Okay, so this is the charge entering the region. It experiences an electric force in the same direction as the electric field lines, since it's a positive charge. And then its magnetic force, its velocity is down. So maybe I'll move here. Okay, velocity is down, curling my fingers into the page, and I get a force that's let's see, is that my right? Okay, so it's that way. So this is the electric force and the magnetic force. So these could be balanced. However, we know that the value of the magnetic force will depend on the velocity. So we would have QE for the electric force equals QVB sine theta. And so for some specific velocities, those 2 sides of the equation can be equal. And if they're equal, the particle will be undeflected. It will have a net force of 0 and continue on in a straight line path. For other speeds where they don't balance, the path will curve because it will now experience a net force one way or the other depending on the speed of that particle. So only charged particles with the exact desired speed that this is set to detect will go through a straight line path and be ejected from the velocity selector. Sometimes a velocity selector is also used with a mass spectrometer. So let's look at the last application here, which is a mass spectrometer. We know this is the cyclotron radius here, mv over qb. Sometimes this would usually start with a velocity selector as well. So the velocity selector process is here, which emits charged particles at a specific speed v. Other ones are kind of going off and not hitting the desired detector. So they pass through the velocity selector, and now all these charged particles of the same speed, generally the same charge as well, are emitted into this region of a uniform magnetic field. So I've chosen one that's into the page, but it doesn't matter. Any kind of uniform magnetic field would be there. The direction they curve depends on the orientation of the field, but the radius where they land on this detector screen will depend on their mass. So this is now a way to filter out particles of specific masses, and this can be used to give information about the masses of atoms or molecules in a chemical solution. So a detector could be here, and it could give you the number of molecules of each mass. or maybe it would target only one mass and then take those masses for another process. So there's many applications of that, but those are three kind of clear, common applications of this motion of charged particles in magnetic fields. All right, let's move on to some examples. Okay, so example 4, an electron moves at 1.4 times 10 to the 6 meters per second through a region where there is a magnetic field of unspecified direction and magnitude 7.4 times 10 to the negative 2 Tesla. What are the largest and smallest possible magnitudes of the acceleration of the electron due to the magnetic field? That's our first question, so let's focus on this. I've got the velocity and the magnetic field on the board. So the acceleration will vary based on the direction of the magnetic force. So if we look at our net force for the electron, that's ma, which is qvb sine theta. So just rearranging that for the acceleration, I have a equals qvb sine theta over m. So at the maximum, this is when sine theta equals 1. Since sine of theta ranges between 0 and between -1 and 1, but I'm assuming we're looking at the magnitude only here. So just between 0 and 1 will be our limits. So the maximum sine theta equals 1. So A is qvb over m to get the maximum. And I'll just plug in those numbers. So we have A max equals Q 1.602 times 10 to the negative 19 coulombs, 1.4 times 10 to the 6 meters per second, and then what's B? Oh, 7.4 times 10 to the negative 2 Tesla divided by the mass of the electron, so 9.11 times 10 to the negative 31 kilograms, to give us an acceleration of 1.82 times 10 to the 16 meters per second squared. And now I would ask you, what is the minimum value? And if you think about it, 0, right? So our minimum will happen when sine theta equals 0. Which is 0. So, and that's the case where the charge is moving parallel to the field. So we know that one. But all right, let's look at B. If the actual acceleration is a quarter of the magnitude in A, what is the angle between the electron's velocity vector and the field? So for part B, now we know that A is actually 1/4 A max. And using this, we can solve for sine theta. So we'll do sine theta equals ma over qvb. So theta is sine inverse, and I'll plug in the numbers here. So sine inverse of 9.11 times 10 to the negative 31 kilograms. 1/4 times our acceleration from, oh, here it is, 1.82 times 10 to the 16. All over Q, 1.602 times 10 to the negative 19 coulombs. V, so V 1.4 times 10 to the 6. And then B. And we'll put B in here, which I'm running out of room, which is 7.4 times 10 to the negative 2. And that should give you an angle of 14.5 degrees. I'll move that a bit closer so you can see. Oh, there we go. Okay, so we have the mass times 1/4 of the acceleration, and then the charge, the speed, and then the magnetic field. You can write it in right there when you have room, which is this value. and then taking sine inverse of that in degrees, we get 14.5 degrees for the angle of the velocity. Okay, moving on to example 5. In an experiment designed to measure the magnitude of a uniform magnetic field, an electron is accelerated from rest through a potential difference of 350 volts in a region where there is no magnetic field, and then enters a region with a uniform magnetic field that is perpendicular to the velocity vector of the electron. The electron travels along a semicircular path of radius 7.5 centimeters and then exits the field. Part A is, what is the magnitude of the magnetic field? Okay, so we have the radius, and eventually we want to use that radius, cyclotron radius, to find the magnetic field. In order to do that, we first need to find the speed of the charge in the field. So I've drawn this here. We have it accelerated at first through a uniform electric field. That's something that comes from the previous section on the motion of charges in uniform electric fields. We know that an electron would accelerate opposite to the direction of the field, which is going to be from low to high potential. But we can solve for the speed through that portion by either using conservation of energy or work energy. So if we look here, we have delta K plus delta UE equals 0, conservation of energy for that isolated system. Splitting that up, Kf minus Ki plus UEF minus UEI equals 0. And I explained that UEI is 0 because it's starting at low potential, and Ki is 0 because it starts from rest. So then if we follow that through, I get 1/2 mv squared equals negative q delta v, and I'm just going to solve for v here. I'll continue up here. So v will equal the root of negative 2 q delta v over m. So that's the root of negative 2 times negative 1.602 times 10 to the negative 19, 350 volts over 9.11 times 10 to the negative 31 kilograms. Turn that a little bit, which will give me a speed of 1.1 times 10 to the 7 meters per second. Okay, so with that we can use our radius to find the magnetic field. So I'm just going to rearrange this formula here to find B. So I'll get B equals mv over qr. So this is 9.11 times 10 to the negative 31 kilograms. The speed we just found, 1.1 times 10 to the 7 meters per second over q. I'm not putting the sign in for q here since I'm getting the magnetic field strength only. And then r, 0.075 meters. Okay, and that gives me a magnetic field strength of 8.34 times 10 to the negative 4 Tesla is our answer for that part. Okay, so basically I wrote in a kind of a non-uniform manner, but we have the first finding the speed here, we get the speed through the acceleration of the electric field. And then up here we can rearrange for B and just use the radius given this radius here to figure out that magnetic field in that region. All right, part B is how long is the electron in the field? So I'm going to have to erase a little bit. I'll erase this here. I'll erase it all. You can pause the video if you need to see that for longer. So, okay. So how long is it in the field? It's in the field for half its period. So one period would be one circle, one full circle for its motion, and it makes only half of the period in the field, which we know from the diagram and the setup of the mass spectrometer. So this is its frequency here. We can calculate its period just by inverting that, 1 over the frequency, 2 pi m over qb. And so then I'll have time is 1/2 of that period. So just pi m over qb, which is pi times 9.11 times 10 to the negative 31 times 10 to the negative 19 coulombs. And then B, which I just erased, let's see what that was, 8.34 times 10 to the negative 4 Tesla. So it's in the field for 2.14 times 10 to the negative 8 seconds. Okay, and now we're asked in part C, what potential difference would be necessary to inject a proton into the field with the same speed? How would its path differ? So before we set up to find the potential difference, our conservation of energy equation, and we had Kf minus Ki plus UEF minus I equals 0. We're going to end up with the same relationship but with different sign, but I'll take a minute to explain why. So since the proton now has a positive charge, it will accelerate in the direction of the electric field, which is from high voltage to low. So now it's going to start with a high voltage, end up with 0, and then we have, and this is electric potential energy, which is QV, and then it will also start from rest. So we'll have 1/2 mv squared equals Q delta V. Here we're solving for the potential difference. So delta V equals 1/2 mv squared over Q. So 1/2, 1.67 times 10 to the negative 27 kilograms. 1.1 times 10 to the 7 meters per second squared over 1.602 times 10 to the negative 19 coulombs. So the potential difference needed in that case is 6.31 times 10 to the 5 volts. It would also have to be oriented in an opposite direction to the potential to accelerate the electron. All right, so how would that change when it moved into the field? Well, for one, it would move in the other direction. Let's look at my diagram again. So if we have this electron moving into the field, and so this is the speed, I curl my fingers into the board, and the force I get up, I have to flip it because it's an electron and it curves down. If it's a positive charge, we don't flip it, we just use the right-hand rule as it is, and it would move up. So it's going to move up. Also, its radius will differ because we have the same speed, Q and B, but the mass is larger, so it will have a larger radii in the field. So maybe something like that, so that it's a little bit larger and going in the opposite direction. Okay, I hope that helps. All right, now moving on to the last example, number 6. The uniform 30 millitesla magnetic field in the figure points in the positive Z direction. An electron enters the region of the magnetic field with a speed of 5 times 10 to the 6 meters per second at an angle of 30 degrees above the XY plane. Find the radius r and the pitch p of the electron's spiral trajectory. So I've sketched that there. We're going to use the formulas for cyclotron radius and pitch, so I put them on the board. And notice that the perpendicular component of the velocity is cosine of theta this time. So we want to check, since the velocity is actually along that z-axis there, and we have this velocity to the y-axis, we want cos of this angle theta to get the perpendicular. So once we have that, we can just plug it in to find r, mv cos theta, cos 30, over qb. So that will be, it is a electron. Okay, so 9.11 times 10 to the negative 31 kilograms. 5 times 10 to the 6. Cos 30, all over Q, and B, 30 millitesla. 30 times 10 to the negative 3 Tesla. Okay, and that gives me a cyclotron radius of 8.2 times 10 to the negative 4 meters, which we can now use in the pitch. So in order to calculate the period, we'll need, again, 1 over the cyclotron frequency, which I did in the last question. So here the period is going to be 1 over f, which was 2 pi m over qb. So let's calculate that first. Okay, so that will be 2 pi 9.11 times 10 to the negative 31 kilograms over q, and 30 times 10 to the negative 3 to get a period of 1.19 times 10 to the negative 9 seconds. I'm almost done. So the last step is the pitch, and we'll just plug in my formula from here. P equals V parallel times T. So this time for the perpendicular velocity we want to use sine. So V sine theta times the period. And that was 5 times 10 to the 6 meters per second. Sine of 30 times 1.19 times 10 to the negative 9 seconds. Which gives me a final period or a final pitch of 2.98 times 10 to the negative 3. And again, what that means is that it travels that far ahead in this diagram. It travels that far along this z-axis in one cycle as it makes one revolution in that perpendicular direction. Okay, that's all for that section. We'll go on to 8.4 next.